Hello again, Galen Pickett, Physics 151 online at Cal State University of Long Beach. So, today we're still working through Chapter 4, and of all the things I've got to tell you in Chapter 4, I think I do need to emphasize a little bit what's going on here in Section 4.8 on friction. So, you have to read the entire chapter to do the problems as I've given them to you, but this section is the one that I wanted to emphasize. So, Chapter 4, Section 8. So there is another approximation that's given here, an approximation that tells you what is the contact force between a surface made out of physical objects. This is a friction force approximation. Now, if you consider an actual physical surface that you put an object sitting on top of, it looks like the object is sitting there perfectly stationary, that there is a force from underneath the object pressing upwards. That's the normal force that supports the weight of the object, and that's just all that's happening. But each of these objects are made out of, these physical objects, they're made out of matter, and that matter is arranged, a bunch of atoms that are arranged on a lattice. Those the lattice is connected by these springs. These springs have a length which you can deduce, and you'll do that in several problems on the problem set. So there is the atoms that are in the block here, and then we've got the atoms that are in the surface, and the atoms in the surface are going to react to the stuff that's supporting it. See how it shrinks a little bit. The springs underneath the load, and in fact the springs up here would also be compressed a little bit. The springs underneath the load are compressed. The ones lateral to the load are not. But this blue surface here, now you see how it's not in it, and in fact it can't be perfectly flat and perfectly smooth, because the yellow object is being pressed into it, say by its own weight. There is this leading edge of the surface, so if I tried to take the block and press it this way, there would be a reaction force that way, and that reaction force we call friction. There is a lateral force. The lateral force that's a part of the contact force between these two surfaces we call friction. And if the two surfaces slide past each other, the friction force, we'll call it the kinetic friction force, in magnitude is some dimensionless number, mu k, times the size of the force that the two surfaces are getting pressed together with, this normal force. And the normal force, I'll remind you, is normal in the mathematical sense, and that it's perpendicular to the surface that we're interested in. It's not normal in the sense of being ordinary or not weird. It is a little weird, but it is perpendicular to the surface. So the friction force gets large in proportion to the load of the surfaces. So if I press them higher, then the yellow surface will invade the blue surface even more, and the blue surface will be pressed down more, and there'll be a bigger lip here for the yellows to catch the yellow surface. Now, what would this mean for a momentum principle application? Here's a flat surface, and now it's not smooth. It's a real surface. It's made out of real material, so there is a coefficient of kinetic friction there. I've got my block here. I'm going to put some force on it, some tension force, some cable that's acting on it, M. Now that block is going to start changing its momentum. It's going to change its momentum in response to that tension, and I'd like to know how. So how is it changing its momentum? dp dt. How is that? Well, we can take a look at this as, again, a statement of the momentum principle. There's the system. It has a mass m. The net force on this thing, I've got a tension. I've got a friction force whose magnitude I do not know. I have a normal force upwards, and I have a weight downwards. One thing I do know is that dp dt is parallel to the x direction. So there's the x direction, there's the y direction. The change in momentum has got a definite direction. So I can ask what the momentum principle says now. The change in the momentum of the system is equal to the net force from the surroundings. These four forces, so I've got the normal force, plus the weight force, plus the tension force, plus the friction force. Now let's see what this means in the x direction. In the x direction, I've got dpx dt is equal to the normal force points directly upwards, so there's a 0x component for the normal force, there's a 0x component for the weight, but there is a x component for the tension force. And there's an x component for the friction force, which is negative points in the minus x direction. So there, I'll call that equation number 1. In the y direction, what I have is dpy dt, which equals 0 because the block stays on the surface. It's got the y component of this velocity is 0 and it stays 0. That's equal to the n component of the normal force is n, the y component of the weight is minus mg, the y component of the tension is 0, and the y component of the friction is 0. That is equation 2. We have 2 equations now. What are the unknowns? The friction force I do not know, dp dx I do not know, and the normal force I do not know. There are 3 things that are not known in this problem. I only have 2 equations that I get from the momentum principle. This, by the way, is the middle of the investigator's work. So I need 1 more equation to have a full set of equations, and that final equation relates the magnitude of the friction force to the magnitude of the normal force. So the magnitude of the friction force is mu k times n, and that is equation number 3. Now I have number of equations is equal to the number of unknowns, and I can get a solution. So execution. Equation number 2 tells me directly that the normal force is equal to mg. So the normal force supports the weight, no surprise there. I'll take that and substitute into equation number 3, so it tells me that the friction force is equal to mu k times mg. And substitute that into equation number 1, that tells me that dpx dt is equal to the tension force minus mu k times mg. And that is the answer we're getting. So now the skeptic review here. The skeptic review, the units of my answer, dp dt, have got to be kilograms, meter per second. That's the units of the momentum, but then if I take a rate of change of that, I get 1/2 so that's the same as a Newton. If I take a look at the units of my answer, I have the units of the tension, and then I've got the units of, now I don't need to take the negative into account here, since I'm adding some physical quantities together. I'm not interested in the actual number, I'm interested in the units here. The units of mu k times m times g. Well, the tension is explicitly some number of newtons, so that's going to work out. It's this one that I've got to worry about. So the units of mu k are dimensionless. The units of the mass are kilograms. The units of g is meters per second squared, which is a newton. So yes, I do have the correct units here. Now what about the behavior? This says that if the friction goes away, if mu k goes to 0, then dp dt x is just t divided by m. Oh, see, I've got the units wrong there. It's t. Yeah, that's fine. dp dt is really just t. If there is no friction. If there is friction, the expression I have here says that the magnitude of dpx dt is smaller if mu is not 0. And in fact, we can get to a case where dpx dt is equal to 0. That would be equilibrium, right? Well, equilibrium for you probably means that the object is standing still, but the technical meaning for equilibrium is that the momentum does not change. That would say that if I pull with a tension that is exactly equal to mu k mg, I can move this thing with a constant momentum. So if I made the breadcrumb trail of how the box moves, it would be moving. So this is the delta x from one time to the other. Delta x divided by delta t is the average velocity. I see these dots. The object moves. It's in equilibrium even with friction. It's just that you need some force to balance the friction force.